This is online Spintronics seminar number 108. The speaker today is Professor Mathias Weiler from the physics department at Technical University Kaiserslautern in Germany. He has earned his PhD at Munich in 2012, where he also earned a Carafas Foundation Dissertation Prize for his work. Then he spent a couple of years at NIST Boulder in Colorado. And after that, from 2014 to 2020, he was a staff scientist at the Walter Meissner Institute in Garching, Germany. He also earned habilitation in 2019 in Munich. And since 2020 has been a full professor of experimental solid-state physics at Kaiserslautern. In 2022, he received an ERC Consolidator grant, and people in Germany may be interested to know that from next April, he will serve as a deputy leader of the Division of Magnetism of the German Physical Society. Mathias is working in spintronics and magnonics. He is interested in controlling spin dynamics by light, sound, temperature, and electrical currents. And his group develops and employs powerful phase-sensitive spinwave spectroscopy tools to quantify magnetization dynamics in magnetically ordered materials and heterostructures. So his talk today will be on chiral magnetoacoustics. I'll hand it over to you, Mathias. Please go ahead.
Okay, Chiral and Xinfan, I mean, first of all, many thanks for inviting me here in this online Spintronics seminar series. Of course, it would be even much better to be back in Colorado, which I enjoyed really greatly, and which is, I think, where Xin and I first met. So with that, let me get started. First of all, of course, I have to acknowledge our funding agencies here on this slide, and then even more important, of course, I have to acknowledge all those who actually contributed to the work that I'm going to present to you here. Well, there's, of course, first of all, the people in Kaiserslautern that are from my group, as well as the group of Burkhard Hillebrands and Philip Pirro, where we are all very interested in studying the interaction of acoustic waves and magnons. There is some very early work that was done in TU Munich, in particular Lukas Dedea was involved at the beginning of the story that I'm going to tell a lot. And then, well, my previous working group, in particular Louis Flacke from the Walter Meissner Institute, contributed to some of the things I'm going to show here. We have ongoing collaborations with the IMAG, the University of Augsburg in particular, IMT Bucharest, and the Institute of Magnetism in Kiev for those things that I'm going to show you here. So the plan for next 40 minutes or so is shown here. So I will start with a brief introduction. Why is it actually interesting, what we are looking at, and what are some technological grounds, and what is some kind of like history of this field. I will then spend some time to talk really about what do I mean by chiral magnetoacoustics. So I will explain the concept of chirality in the sense that we are using here. Then I will come to the largest part, which is talking about the non-reciprocal effects that can be observed in magnetoacoustic devices. And then finally, also touch very briefly on nonlinear phenomena that we are observing. So let's get started. So here in this Spintronics community, it should be very clear for everybody that this is a fantastic field. And magnonics is a very important subfield of Spintronics. Magnonics deals with the use of spin waves for information processing. So one can use spin waves and encode information typically in the phase of the spin waves. And because those are waves, they can interfere with each other. So then one can use that to build logic elements that are based on wave interference. And there's some recent review papers over here where you can find all the details. On the same footing, there is also sound waves that are technologically very intriguing, and they're even much further developed already than the field of spin waves, because all of us, we use dozens of filters in our mobile phones for mobile communications, and these filters, they are based on sound waves. Typically either surface acoustic waves or bulk acoustic wave filters. And an example of such a filter performance is shown here on the right-hand side. So this is a filter, smartphone filter for GPS signal. It is about at 1,000 something megahertz over here. And you can see that this filter has a very low insertion loss, about 2 dB, and it has a very high out-of-band rejection of about 50 dB, and all that in a miniaturized package. Okay, so that's why this is a huge market, about 4.5 billion US dollar a couple of years ago. Well, now the idea of the magnetoacoustics is, well, let's combine these two fields. Okay, and why is that promising? Well, that is promising because if you look at a typical wavelengths of a microwave photon in the gigahertz regime, and that's where we want to work, it's in a centimeter range. Whereas both the phonons and the magnons, they have wavelengths in the micrometer scale. And that means it has great potential to miniaturize microwave devices, because the typical non-reciprocal microwave devices like a circulator or an isolator that are used today, they're rather large. They're centimeter scale devices, and that is because the microwave photons are centimeter scale. So that's a potential to miniaturize these devices down to the micrometer scale. There is also another perspective, in particular for the field of magnonics, and that is if there are sufficiently large coupling phenomena between the phonons and the magnons, one should be able to use phonons to very efficiently excite magnons far away from k equals 0, where one can typically excite those efficiently directly with microwave photons. So the prototype device that one looks at in this field is based on surface acoustic waves. So surface acoustic waves, macroscopically, well, these are earthquakes. So these are Rayleigh type earthquakes. And microscopic, these are the type of waves that are used in these mobile communication filters. So Rayleigh type surface acoustic wave consists of a combination of shear strains epsilon xz and pure strains epsilon xx over here that will lead to a deformation of the surface of this half space shown here. They are also technologically relevant because it is simple to excite and detect these surface acoustic waves. And the means to do that are so-called interdigital transducers, and that are thin metal gratings and thin film technology deposited on top of such a piezoelectric substrate. And then one uses the piezoelectric effect by applying a microwave frequency voltage to these interdigital transducers to launch acoustic waves. And in the reciprocal effect, one can also detect these acoustic waves with the very same structure again. So the output interdigital transducer over here. And now the field of magnetoacoustics in its most simple representation, it takes such a surface acoustic wave filter from mobile communication and then deposits a thin film of ferromagnetic material in the propagation path of the acoustic wave. And that will then lead to a periodic elastic deformation of the ferromagnetic thin film. And in total, we can then interact between the spin waves in this ferromagnetic thin film and the sound wave propagating here, and the electric field generated because the substrate is piezoelectric that can then be picked up. What I now want to do is very briefly talk about what are the origins of this interaction. So why do we actually get an interaction between sound waves and spin waves? And I want to do so by looking back a bit in history. And the first work that really dealt with this interaction of spin waves and ultrasonic waves dates back to Kittel, 1958. And in this theory work, what Kittel introduced was the magneto-elastic free energy contribution, where one can see that a pure strain and also a shear strain modify the free energy density of such a thin film, because either pure or shear strains modify the magnetic anisotropy of the material. And that is due to spin-orbit interaction. One can then derive, as Kittel already wrote, from the free energy, one can derive an effective field. So it's the magneto-elastic effective field. and that's the derivative of this free energy with respect to the magnetization direction. And in his work, Kittel made this assumption that one can neglect or that the mx and my components are much smaller than the mz component. And then one sees that the dominant components that remain are those that contain an mz, and those are here, these shear strain components. So that is kind of like the original idea. There should be an interaction. Whenever there is a strain, it generates a virtual magnetoelastic field, and one can easily estimate the magnitude of that field that can be achieved. And the strains in the surface acoustic wave devices is typically in the order of 10 to the minus 3, and that gives a magnetoelastic field in the order of about 10 millitesla. So that's already very promising. One can then take this magnetoelastic field, one can insert it in the total effective field, and then solve the Landau-Lifshitz equation. And by that, one immediately sees that this will cause magnetization dynamics. First seminal experiments that go in that direction were done very briefly afterwards, the Bömmel and Dransfeld experiment, where they took a quartz rod that on one side had a nickel film, and the quartz rod was used to connect two microwave cavities with each other. And what they did is they used kind of like this input lead here and excite the microwave in this first cavity. One excites the ferromagnetic resonance of the nickel film, and because of the magnetoelastic coupling, it launches a sound wave. And because the quartz is piezoelectric, that leads to an electric field on the other side of the quartz, and that then couples to the second cavity, because here it is placed in an antinode of the electric field, whereas on the left-hand side, it's placed in an antinode of the magnetic field. And they showed in this experiment that this can be used to transmit microwave power by taking the detour through phonons, which is in the end identically what we do when we transfer phonons using interdigital transducers nowadays. Going a bit on in history, 1976, so there was a follow-up experiment at rather low frequencies, 100 megahertz, far below the FMR frequency, in this case also a nickel film. There was this experiment over here where the authors showed that because the static rotation of the magnetization, when one varies the external magnetic field, there was a field that was applied in plane, but a perpendicular magnetic anisotropy thin film of nickel. So you have a region where the magnetization pointing at some oblique angle to the out of plane direction, and that via the delta E effect causes a modification of the elastic constants of the nickel that depend on the orientation of the magnetization. So there was already shown an influence or a coupling between the surface acoustic wave and the magnetization, but this was, so to say, static. One can then go on, and there is experiments here a bit later that showed, well, indeed, if one increases the frequency of the acoustic wave a bit, one can basically use the magnetoelastic field as what they call a Tickle field to measure the magnetic hysteresis of such a nickel film. And they showed that their experiments that they recorded in the surface acoustic wave spectroscopy closely mimic what they do in a standard AC, susceptibility measurement of the same nickel film again, right? So they established this idea that the surface acoustic wave really generates such a magnetoelastic field as predicted by Kittel. Our experiments kind of later, we then showed that if one increases the frequency of the acoustic wave such that it matches the ferromagnetic resonance frequency of the elastic film, one can then get a resonant coupling between the magnetic excitations in this magnetic film and the surface acoustic wave. So we still see this hysteretic behavior, the switching behavior over here was shown on the previous slide already, but now additionally, we also see this absorption which occurs, which we ascribe to the interaction of the sound waves and the spin waves at the mutual crossing point of their dispersions. What distinguishes this observation from the previous ones is that there is a very peculiar angular dependency of this interaction here. And that dependency of the acoustically driven magnetic resonance that can be traced back directly to this approach originally proposed by Kittel, to deriving the driving fields of this interaction from the change of magnetic anisotropy that is induced by the oscillating wave. Now, I don't want to go into the details of that, but I want to highlight some, well, seemingly very minor thing here for this talk. And that is, if you look closely, then you see that the dip over here at positive field is a bit less pronounced than the one here at negative fields. Okay, so it might just look like, okay, this might be measurement uncertainty, but it's actually not. There is a non-reciprocity in this experiment, very weak, but now in recent times we have shown that this non-reciprocity can be as large as several orders of magnitude. Right? Okay, and that's what I want to discuss next. Why can this coupling actually be non-reciprocal? And that brings me to the next part of this talk, and that is the chirality. So chirality is very well known from chemistry, right, or just from our hands that are chiral objects. And what I want to remind everybody here, it's chiral because basically the back side of our hand and this side of our hand, the inside of our hands are different, right? And that's also really important for this chiral object. It's that this part of the molecule sits in front of this part here, okay? So you need this three-dimensional object somewhere, or you can describe it in general. You need kind of like three vectors that are orthogonal to each other that describe the object so that it can be chiral, okay? That means flat hands, like these wooden ones here, they're not chiral, right? Because their back and front side are actually identical, okay? So these would be an achiral object. Okay, so now let's look at this chiral properties with regard to spin waves and sound waves. So let's start with sound waves. So a sound wave, I'm taking here a circularly polarized sound wave, so a combination of compressional and shear waves, because this is what we deal with in the Rayleigh waves that we typically use. Such a sound wave, taking kind of like the description previously, it can be described by two vectors. One is the direction of propagation of the sound wave, and the other one describes the helicity of the rotation of the lattice atoms. You can also look at a spin wave, and we get a very similar picture. There is the propagation direction of the spin wave, and there is the helicity of the precession. So both of these objects are not chiral, right? So neither spin waves nor sound waves are chiral objects. That changes, however, if one looks at surface acoustic waves, and these sound waves, then we get an evanescent character because there is a surface on one side that breaks the symmetry. And that leads to this additional vector in here, and that can also be done for surface spin waves in the very same manner. So if you have surface waves, so be it like sound waves or spin waves, these are actually chiral objects, right? So for the spin waves, the famous example is the Damon-Eschbach surface wave, and that is then a chiral wave. Now, there is chirality and there is non-reciprocity, and those two things are not the same. Okay? So a sound wave can either be achiral, like shown here, and reciprocity can be seen if one applies a time reversal operator or any operator that just rotates the construct in space or any combination thereof, and you can recover the mirror image. And here, that works for the time reversal operator. Right? So if you take the time reversal of these lattice motion here, you get exactly the counter-propagating sound wave. Okay? And that means sound waves are reciprocal. Okay? And that doesn't change if you introduce a surface. So surface acoustic waves are actually chiral objects that are reciprocal. And that means if you have two individual transducers and you send an acoustic wave from one side to the other or this side, you will obtain the same transmission. Okay? And that's what one typically does in this experiments over here. Right? So Rayleigh waves are chiral, but they are reciprocal. Now, going back to spin waves, so if you look at a spin wave over here, and we want to map this spin wave to its kind of like counter-propagating part, then what is different about the spin wave is that the helicity of the precession, which here in this case is counterclockwise, is set by the direction of the magnetization and not by the propagation direction of the wave. Okay? Well, that means to obtain the counter-propagating wave, we have to do a time reversal operator. That will mean that all the spins rotate in the opposite direction, like that. And then we still have to do a rotation. Okay? And then we recover this wave over here. Okay? So we rotate the entire picture like that. And that means such a spin wave is not chiral. There's no surface in this wave. It's a bulk spin wave. And it is also reciprocal. Okay? And that changes if we introduce the surface. Right? So if you introduce the surface, then the symmetry operation here, this rotation about the x-axis, that would be needed to go from this image to this image, you would have to basically rotate it about this red arrow over here. And that doesn't work anymore if there's a symmetry breaking along this up direction. Okay? And that means that in general, surface spin waves, they can be chiral and non-reciprocal. Okay? So you know that from the Eschbach waves that they already can be non-reciprocal. And one other famous example of non-reciprocal surface spin waves is the spin waves with Dzyaloshinskii-Moriya interaction, right, where the DMI at such an interface or such a surface here breaks the inversion symmetry, and that can lead to a non-reciprocal wave. And that means that the spin wave dispersion can shift from the standard parabolic behavior shown here in the black dashed lines to a shifted one to this blue one over here. Okay? Now what's actually really intriguing about this magneto-acoustic waves is combining reciprocal sound waves and reciprocal spin waves. And that is what we do in many of the experiments. We take Rayleigh surface acoustic waves. They're chiral, but they're definitely reciprocal. And we take spin waves in very thin metals. They're only a few nanometers thick. And that means that the spin waves in these very thin metals, they have a very low dipolar interaction. They basically only see the exchange interaction. And they're also reciprocal. Okay? So we have reciprocal sound waves and reciprocal spin waves typically. But this reciprocity of these two waves to go from counter-propagating waves to each other, it requires a time reversal symmetry operation for sound and a time reversal plus rotation symmetry operation for spin. And that means if I combine these two waves, which is what we do in the magneto-acoustic wave, if you let them couple, then there is no symmetry operation anymore that can map the wave here on the left to its counter-propagating part. Okay? And that means we can indeed combine two reciprocal waves, reciprocal sound wave and a reciprocal spin wave. We let them interact with each other, and then the magneto-acoustic wave that results can, by symmetry, be non-reciprocal. That doesn't mean that it has to be non-reciprocal, but it means it's allowed by symmetry. Okay? And that's very fundamental for all the things that we're looking at. So we can combine two waves individually reciprocal and then get non-reciprocal effects. And that's what I want to show you. Okay, so this is the non-reciprocal effects that we observe in magnetoacoustics. Okay. So a typical experiment is sketched here. So here in this experiment, we again start with a Rayleigh surface acoustic wave. And the device is sketched over here. So we have interdigital transducer 1 and interdigital transducer 2. And in the propagation path, we have our ferromagnetic thin film, which is either cobalt iron boron or a bilayer of cobalt iron boron platinum over here. And now using our vector network analyzer, we can now measure the transmission from up to down or from down to up. And that is when we measure either S21 or S12. And we can apply an external magnetic field. So here we apply it in the film plane. The frequency of the surface acoustic wave is here 7 gigahertz. And on the right-hand side, there is the experimental results that we obtain if we just use a blanket cobalt iron boron thin film. Okay? And in this cobalt iron boron thin film, having the surface acoustic wave passing through it, what we observe is a non-reciprocal behavior. So if we say we switch the direction of propagation of the spin wave, of the sound wave, sorry, we go from the red curve to the blue curve. That corresponds to acoustic wave like that or acoustic wave like that. And you can see that the transmission is definitely different at this location. It's the same kind of like out here, where we are at a point where there's no interaction between the acoustic wave and the spin wave. Okay? But here where there is an interaction on, it becomes non-reciprocal. Same over here. And then the Onsager relations dictate that this blue kind of like curve over here, a positive field, is the same as the red, a negative field, and vice versa. Okay? And that's what we observe. Another question is, well, it's allowed by symmetry, but why is it now really non-reciprocal? Okay? And well, the model that we use to explain the non-reciprocity goes as follows. So we start from a Rayleigh acoustic wave. And that means we have the lattice motion on such a circular or elliptical trajectory at the very surface of this material. And that means there are strain components that are pure strains and that are shear strains over here. And we can write down the effective field that is generated by the magneto-elastic interaction. So the effective field that this thin magnetic film sees here, because you change the strain and because there is spin-orbit interaction in the magnetic thin film, with B, the magneto-elastic coupling parameter. Okay? And what one obtains from that is, well, if both of these these strain components here are non-zero, and they are if you have like an elliptical motion, because otherwise it would just be linear polarized like that or linear polarized like that, then that means that also the driving field, if you kind of like choose some orientation of the external magnetic field where both of those are non-vanishing, will be elliptically polarized in general, right? Okay. And now we have an elliptical polarization of the driving field. And in this case, I take it to be counterclockwise. And if you also have a counterclockwise precession of the spins, then you get good coupling. Okay. If, however, the ellipticity of the driving field is actually opposite, so here clockwise to the still counterclockwise propagation precession direction of the magnetization, because we only inverted the propagation of the surface acoustic wave, then you would expect poor coupling. Right? Okay. And that can in principle explain the non-reciprocity that we observe here in experiment. So it looks like at that point we could say, well, case closed, we understand what's going on. However, there is a problem with that interpretation. And that is that it has been shown here by Sadamichi Maekawa and co-workers already in 1976 that, well, the shear strain at the surface of such a Rayleigh acoustic wave, it actually should vanish. Okay? And that's because it's a stress-free surface. Okay? And that means there should be no out-of-plane driving field, but rather you would expect a linearly polarized driving field from magneto-acoustic interaction. And then there should not be any non-reciprocity. Okay? However, what comes to the rescue here is the so-called magneto-rotation. Okay? And the magneto-rotation is really directly this rotation motion of the individual lattice atoms. That gives a rotation that is described here. So the only difference to the shear strain is the sign here, so it goes from plus to minus. And this rotation also exists at the surface, or it is even maximized at the surface. And in magneto-rotation, you can now imagine that there is an interaction with the ferromagnetic thin film, because what it does is it's basically like bending the thin film of the ferromagnet. And if this ferromagnet has a hard axis ferromagnet, as we typically have, easy plane hard axis ferromagnet, in plane magnetized, it means you're basically modulating the anisotropy axis direction with the frequency of the acoustic wave. Okay? And that's also why this magneto-rotation field, it contains the strength of the anisotropy field, which for a thin film limit is just saturation magnetization divided by 2. Okay, and that's what's in here. Okay, and what's kind of like really funny about this magneto-rotation thing is it does not require magneto-elastic interaction, right? It's really just a modulation of the anisotropy axis. So this works even if your magneto-elastic coupling, which is described by the parameter B, is exactly 0. Okay, It does not require magneto-elasticity, does not require spin-orbit coupling. Okay? And that comes here to the rescue because this, well, recovers the elliptical precession of the total driving field. Okay? And that has been experimentally realized first by Mingrang Xu and co-workers about 2 years ago, and they used the thin film of cobalt iron boron. Okay, so very similar to what we looked at, and they showed that indeed they observe a strong non-reciprocity of the transmission from left to right and right to left, so identical to what I showed you before, and they ascribe this non-reciprocity to the existence of such a magneto-rotation coupling. Okay? And well, basically at the same time, we also published very comparable results of cobalt iron boron, well, the only difference being the thickness. So we had 2 nanometers, they had 1.6. And well, we found that indeed, if you look very closely, then the idea that the epsilon xc is identical to 0 at the surface is not completely true if your ferromagnetic film is kept. Okay, which it was here and which it also was in our experiments. Typically, you cap to prevent oxidation, and even only like half a nanometer of capping will introduce a non-zero epsilon xz anymore. And you can read it up here in this publication. If you do it like quantitatively, then for typical capping layers, you will find out that both of these effects are very comparable in magnitude. Okay? So they both contribute about 50% to this non-reciprocity. Okay. So now, well, technologically, if you have such a non-reciprocity, I mean, that's all nice from the fundamental physics side. But if you want to use this for a device, you want to make a device that has as large non-reciprocity as possible. And then you can imagine that could be used as a miniaturized microwave isolator, for instance. Right? Where you can have microwave power flowing from left to right, but not from right to left, for instance. That would be extremely useful, right, if that can be realized, because it can be miniaturized to the micrometer scale. It's based on a very, very established system, right, which is exactly the system that is used in the frequency filters in the mobile phones. So that would be a technologically very relevant microwave isolator. So now the question is, how can we actually optimize it? And the first thing that we thought about to optimize it is, well, we can now make the system a bit more complicated by adding platinum to it, and by that making the spin wave dispersion itself already non-reciprocal. Okay, and that might help our case here. And indeed it does. So if you look at the transmission data over here, you can see now here there's a non-reciprocity not only in amplitude between the red, the red and the blue curve over here, but also in resonance field, right? Right, and that's because we now have a non-reciprocal spin wave dispersion. So to obtain the same frequency, we have to modify the external magnetic field for counter-propagating spin waves. Okay? And this non-reciprocity due to the Dzyaloshinskii-Moriya interaction, well, this form of this expression here, right, that comes from this work, this theory work shown here. So indeed, when we actually do these experiments and we take the spin wave non-reciprocity due to the Dzyaloshinskii-Moriya interaction into account, and you can see here our experimental data. You see here is the cobalt iron boron that I showed you previously, and you can see there is an amplitude non-reciprocity. If we take some direction of the external magnetic field, then we compare this point to the same point for the opposite propagation direction of the surface acoustic waves. There is a clear difference in amplitude, but there is no difference in the resonance field. And that changes if one additionally introduces the platinum, then you get also a shift of the resonance field. Okay? That can be quantitatively evaluated. From the shift of the resonance field, we can extract the effective or the volume average Dzyaloshinskii-Moriya interaction constant, the effective. And as you can see here, the effective, as you would expect, it scales as 1 over thickness of the ferromagnetic material, here the cobalt iron boron, because it's an interfacial effect coming from the platinum. And the absolute values, well, they agree well with those that have been previously published as a Dzyaloshinskii-Moriya constant for the cobalt iron boron platinum system. And of course, if you only look at bare cobalt iron boron, it's basically zero, what you observe here. Okay? So that could already help to increase the non-reciprocity, but the non-reciprocity here that we observe in total is still rather weak. It's not technologically useful. It's a couple of dB. So we basically went from a non-reciprocity of about 1 dB to one that is about, well, a bit less or a bit more than 2 dB. That's kind of like nice, but not useful. Okay. So then, we thought about other ways to increase the spin wave non-reciprocity further. And one can, instead of relying on Dzyaloshinskii-Moriya interaction, rely on classical dipolar interactions. So it is very well known that in dipolarly coupled bilayers of ferromagnetic thin films, and here we take permalloy, cobalt iron boron, and the gold is only here to prevent exchange coupling between the cobalt iron boron and the permalloy. And in such layers, it is very well known that the spin wave dispersion shown here becomes highly non-reciprocal. There is a complication because you have these two ferromagnetic layers, and that is you get like a acoustic and then optical mode of the spin waves here. But as you can see here, in particular, or both of them are actually non-reciprocal, right? So here you end up at 4 gigahertz, and here you end up somewhere below 4. Same for the acoustic mode. Okay? Now that means what we would expect when we let the system interact with the reciprocal dispersion of the surface acoustic wave. We should get basically as a function of frequency these 4 different absorption peaks, right, corresponding to the individual crossing points that you get here, right? And you get the 4 different ones because it now depends on the direction of propagation of the acoustic wave. So we can again do that in experiment, and yes, indeed, we do observe for given orientation of the external magnetic field, right, you observe this 1, 2, 3, 4 interaction points. Okay. We can see that well, we have our experimental data, and the simulation is basically also done using a model, and purely analytical phenomenological model that we developed that just takes this spin wave dispersion into account. You can see that I would say we have here full quantitative agreement with from the observation and the model here. And if you look now here into the non-reciprocity, then we have to define an operating point. So we have to say if we want to use such a device, well, we could integrate some permanent magnet and thin film technique on this on such a device as well, and then say, okay, we get some orientation of this field and we get some value of the field, but that is something we can obviously not change once the device is made, right? So we could, for instance, operate it here at this light blue point or at this kind of like purple point over here. And then what we look at is microwave transmission from left to right versus microwave transmission down here from right to left. Right? And there is a very clear difference. Okay, and this non-reciprocity in such a structure that can now reach 35 dB, and that's already like a useful value. We have some insertion loss compared to a device without the magnetic film. When you put the magnetic film here, you see that the performance is about 1 dB worse. Okay, and then of course we have the bare performance of these two IDTs, and that of course goes back to what I showed you before. That's exactly the insertion loss you get when you have like a surface acoustic wave filter in your mobile phone, which well, in the best commercially available ones is apparently about 2 dB, which for some that are found in the scientific publication at the frequency that we operate can be about 4 dB. Okay? And of course, there's further possibilities to optimize this non-reciprocity, right, by changing the thicknesses of these individual layers, for instance. Right. Okay. And in total, what's kind of like nice about this is that optimizing the non-reciprocity using this dipolar interactions does not require you making the films extremely thin, right? Whereas you need to make the films extremely thin if you want to optimize non-reciprocity with DMI, but that would also increase the line widths, right? So that it will be challenging just with DMI to really obtain a large non-reciprocity. So now, so far, I talked exclusively about Rayleigh acoustic waves. Well, there is also other surface acoustic wave modes that can have potentially very beneficial properties. And I want to briefly look into that and see how that affects the symmetry of the magnetoacoustic interaction. And by symmetry, I mean, what should be the optimal direction of the external magnetic field relative to the propagation direction of the surface acoustic wave to optimize the interaction of surface acoustic wave and spin wave. Okay? So we had already looked at that at the Rayleigh mode. Here it's a substrate, it's lithium tantalate, and that supports a Rayleigh mode that is well known with this sound velocity of about 3,000 meters per second. But it also allows for a horizontal shear wave mode. Okay? And the horizontal shear wave mode, meaning it's a wave that basically propagates like this. Right? It's a pure or almost pure shear wave, as shown here in our COMSOL simulations. Okay? And the nice thing is, well, this system basically supports both. Right? So for instance, one can do here time domain spectroscopy of the transmission of surface acoustic waves from left to right. And then one sees that after some time delay, about after 400 nanoseconds or so, you see the arrival of the shear wave, and then it takes a bit longer, and then the Rayleigh wave arrives because it's slower. Right? So you can pick a frequency, for instance, 3.5 gigahertz. So you get a very nice shear horizontal wave, but you also get a Rayleigh wave at the same frequency. Okay? And now we can fix this frequency to this 3.5 gigahertz. Okay? And then we can look at the symmetry of this magneto-elastic interaction. So what should be the ideal orientation of the external magnetic field to get an interaction? And you can see here, if you use the shear horizontal wave, that the ideal orientation of the external magnetic field is basically along x, along the propagation direction of the sound wave, and with that the spin wave, or exactly along y, meaning orthogonal. Okay? And that's different to that what we observe in the very same sample, in the very same measurement even, with the Rayleigh wave. Because that tells us, well, the ideal orientation of the external magnetic field should be about 45 degrees, or the magnetization has to be as 45 degrees to its propagation direction. Now, those people working with spin waves, well, they will kind of like this, right? Because this allows you to operate such a device when you really want to interact with spin waves, in particular in either the Damon-Eschbach geometry, which here would be the 90 degree, or in the backward volume geometry, which here would be the 0 degree. Which are these orientations where, unfortunately, using a Rayleigh wave, there is absolutely no interaction. Okay? So one further thing to look kind of like towards potential applications of this is, well, making it CMOS compatible. And well, to do that, collaboration here with the IMT in Bucharest, well, we looked at samples where they deposited here a nickel film with a gold capping layer on top of a scandium aluminum nitride piezoelectric layer, and everything is made on a standard silicon wafer. Okay, so it's thin film technology on silicon, so it's CMOS compatible. And well, in that system, we also get two types of waves. So we get a Rayleigh wave, and the second one here at about 8 gigahertz, that's a so-called Sitsawa wave. So that's a form of, like, well, not really surface acoustic wave, but like a mode that requires an interface between two materials with different mechanical properties, which in this case here is the scandium aluminum nitride and the silicon. Okay. And here again, we observe that we can do this magneto-acoustic interaction. It's non-reciprocal, right over here for the Sitsawa wave, right? You see the non-reciprocity, also for the Sitsawa wave, also for the Rayleigh wave, a bit less pronounced over here. And well, that means, in principle, we could now go and do all the development that we did on lithium niobate, also on a CMOS compatible piezoelectric material. Now I'll take like the remaining 2 minutes to very briefly touch on nonlinear effects. So nonlinear effects are a very important field or very important topic in the field of magnonics. So magnonics really thrives from nonlinear interactions between magnons. And well, we question ourselves, well, can we actually use surface acoustic waves with sufficiently high amplitude to drive nonlinear effects in here, for instance, a thin film of cobalt iron boron, which has a damping that is typically so high that it will be very challenging to use a microwave antenna to excite nonlinear spin waves in this material. Okay? So we use Brion light scattering spectroscopy with spatial resolution to measure locally the excitation of spin waves in this cobalt iron boron film under the excitation or under the driving by the acoustic waves launched at this IDT. One first thing what one sees is, well, if we put a certain microwave power to the IDT and then scan the external magnetic field, we see there is a certain resonance field here, about 8 millitesla or so, where one sees an increase of magnons. Okay, and one sees, well, this peak seems to shift when we increase the microwave power. Okay, heating effects, whatever, that's probably what one would expect. Okay, and now we look at that a bit closer. So we set the external magnetic field here to 6 millitesla. That corresponds to the peak here in the low driving power regime. And then we sweep the microwave power at this external magnetic field. And what one sees is, well, first of all, at low powers, there's only one frequency. But then eventually, if one increases the power, there is other resonance frequencies appearing. It's difficult to see on the color code, and that's why we here have integrated the intensity at these frequencies. Right, you can see there's a very clear threshold of about 15 dBm of microwave power, where we obtain additional resonance frequencies. And they can be explained here as a confluence process of two phonons here that then generate two magnons under conservation of frequency and momentum. One can also go to a magnetic field that is actually below the resonance field, here 2 millitesla, and do the same experiment again. And then what one sees is one actually excites, in this case, like a whole slew of different magnon modes in a nonlinear fashion. Okay? And these magnon modes, they can also be described either by a direct pumping by the acoustic wave, or by a process where the acoustic wave is first converted into a magnon in linear fashion, and then we have a nonlinear magnon process. These findings are currently on the archive. So with that, I'd like to come to the end and conclude. So in summary, I hope I could show you that these magneto-acoustic waves, there are interesting things because they can be chiral and non-reciprocal. Right? So this non-reciprocity, there's two important effects that contribute to it. It's magneto-elasticity and the magneto-rotation effect. And we can also use such a setup to acoustically do spectroscopy of the strength of Dzyaloshinskii-Moriya interaction. We can enhance the non-reciprocity by enhancing the spin wave non-reciprocity in bilayers. We can also go and study nonlinear interaction effects. I very briefly want to do a shameless self-advertising. So if you know somebody, or if you yourself are interested in working in this field, we currently have open positions. It's on the Spintronics website. Spintronics seminar website. So please have a look. So thank you very much for your attention.
Thank you very much, Matthias, for this exciting talk. Let's thank him by using the reactions buttons in Zoom. So we'll now switch to questions. If you have a question, please raise your hand in Zoom and wait for me to call upon you. And please don't wait for the previous question to be answered. If you have a question, please just keep your hand raised. And if you are in Twitch, you can just type your question in the chat box and I'll read it for you. Question, please. There's a question in Twitch. Are surface acoustic waves used for controlling magnetic skyrmions?
Okay, very good question. I would say yes. There are publications that show that one can use surface acoustic waves to nucleate magnetic skyrmions in thin films. And actually, in this very project over here, one part of that is actually using surface acoustic waves to transport and to sort magnetic skyrmions. So I would say, very good idea. I like the idea. And there is kind of like experimentally so far only like generation of magnetic skirmions, of strongly pinned magnetic skirmions. But I see that there is great potential to move magnetic skirmions with acoustic waves. Yes.
Okay, thank you. Shin, please go ahead.
Thank you, Matthias, for a very, very interesting talk. Can you comment on that, like spin waves can carry angular momentums? Do you expect the chiral SAW also carries angular momentum that can interact with, like spin torque type of things?
Okay. I mean, you're basically kind of like predicting all these proposals that are submitted, because yes, totally. I mean, if you have like a sound wave like depicted here, then of course that comes along with an orbital angular momentum, right? Because the lattice atoms basically, well, do describe a circle, right? So that has a mechanical angular momentum that would point towards us or away from us, depending on the sign. And of course, I at least would very much expect that it should be possible to transfer this angular momentum from the lattice to the magnetic system. Right? I am not aware of any experiment that has shown it. I'm not even aware of a real theory that describes it, apart from some abstract ideas.
I see. Thank you. That's very exciting.
Okay, Tony Kent, please go ahead.
Hello, can you hear me all right?
Yes.
No, not used to Zoom very much. Yeah, so clearly working with surface acoustic waves, they're somewhat limited on the sort of frequency you can reach. So for higher frequency work, people with filters and things, people tend to work with bulk acoustic waves, but the symmetries are all different in this case. Can you comment a bit on what the prospects are for sort of applying bulk acoustic waves in this kind of system?
Yes, so we're also working with bulk acoustic waves. I don't have published data, and I didn't want to show kind of like a lot of unpublished things here. It works. So the symmetry of the bulk acoustic waves, you typically, in the simplest case, right, your wavelength is set by the thickness of your piezoelectric multi-layer stack somehow. You typically get either pure shear strains or either pure compressional strains, right? And then you can take the very same symmetry arguments that has already been developed by Kittel, and you can apply that, and by that then calculate what the driving field should be. What we see in experiment is that this describes it quite well still, also for the bulk acoustic wave. I think the big problem with the bulk acoustic waves might be to really get this kind of like chirality, right? To really get kind of like this elliptical lattice motion. Because as far as I'm aware, kind of like the easily available modes are the pure compressional waves or the pure shear waves, right? That don't allow for these fancy physics. I would not kind of like give up surface acoustic waves quite yet. And that is mainly due to nonlinear interactions of phonons themselves. So we can, in the lab, quite easily achieve frequencies above 20 gigahertz of these surface acoustic waves.
Okay, thank you very much.
Still be kind of like helpful.
Yeah, thank you.
Thank you. Let me ask a question. So is it possible to do some sort of gating to tune the frequency of those waves or coupling to magnetism, perhaps by tuning the DMI, and make the devices that you were discussing tunable?
So I'm not aware of actual experiments that have shown that. What has been shown experimentally is that you can tune the Dzyaloshinskii-Moriya interaction either by strain or by electric fields, right? In such kind of like similar thin film bilayers. So that means you would basically expect that you can tune this non-reciprocity in the resonance field by gating, right? Okay. I see a bit of the problem with doing that with the DMI, that basically have very large line widths, and right, and you kind of like tune it a bit. So I'm not sure it will be technologically really viable in the end to get a tuning of the DMI that is sufficiently strong that you basically can switch on and off non-reciprocity, right? Might be very challenging to do so. It might be easier to do to actually tune it not by electric gating directly, but by using static strain again, right? By tuning the piezoelectric material that you have anyway with a DC voltage, you kind of like change the anisotropy of the material that you have, change the anisotropy then of the magnetic material with a DC strain, and then use that to tune it. My guess would be that this could be the more viable approach than tuning the DMI directly with an electric field.
Mhm.
Yeah,
Okay,
but
I see.
we have not done any experiments in that direction.
I see. Thank you. Are there any further questions, please? Okay, it looks like we're out of questions, so let's thank Mathias again for this interesting talk.